In section 2.3, we have some less common ways of organizing and displaying quantitative data. These are ways that the data might be organized or displayed, but they're less common than like the histogram or the frequency and relative frequency tables and so on. The first thing that we want to talk about is called a frequency polygon. Now, a frequency polygon, I'm going to go ahead and talk about this, is a graph that uses points connected by line segments to represent the frequencies for the classes. So instead of using bars, we use points, and then we're going to connect those points with line segments. It is constructed by plotting a point above each class midpoint on a horizontal axis at a height equal to the frequency of the class. Next, line segments are drawn connecting consecutive points. Two additional line segments are drawn connecting each end of the graph with the horizontal axis. Now, I use the term midpoints right here. So we need to define a class midpoint. So in general, a midpoint means it's a value that's in the middle. And so the midpoint of a class is the value that's in the middle or the center of a class. So a class midpoint is the sum of consecutive lower class limits divided by 2. So if you take a look at this data right here, my example, construct a frequency polygon using the parking and camera fines data from section 2.2. So this was data we used in section 2.2. We created a histogram from it. We created a frequency and relative frequency distribution. So if I want to create a frequency polygon, then the first thing I'm going to have to do is find the class midpoints. Now, I'm going to tell you, statistics is still evolving. And so if you look at different resources, they may define class midpoint slightly differently. Some resources say average the lower limit and the upper limit of the class to find the midpoint. So some resources would say take 60 plus 89.99 and divide that by 2 to get the midpoint. Our textbook doesn't do that. Our textbook says average the lower limit of the class with the lower limit of the next consecutive class. So I'm not going to average 60 and 89.99. I'm going to average 60 and 90. So if I take 60 plus 90 and divide that by 2, that's 75. So I would say my class midpoint is 75, not 74.995. Again, just to be clear, if you looked on the internet and searched class midpoint, they might very well define it this way. You might find a resource that's defining it the first way that I showed you. We're going to do the second way. Which is better? It's debatable. Personally, I'm in the camp the way we're going to do it. Since we're talking about continuous data, well, usually it's continuous data that we're dealing with, then that data doesn't really stop at 89.99. For example, if it's continuous data, it goes on to just before 90. So in my opinion, the way we're doing it is the better approach, but someone else could disagree with me, and that's fine. So anyway, I've got to find all the class midpoints. So now I'm going to average 90 and 120. And so that's 105. Next, I'm going to average 120. Whoops, I forgot my parentheses. 120 and 150. And so that's 135. And so on. Now, I will tell you, when we did this problem by hand in section 2.2, I used a different class width than what I used in my summary right here when I created this. I used a class width, I think we used a class width of 25 instead of 30. I'm using a class width of 30 here. So this isn't going to perfectly match what we did with the histograms, but it's very similar. If these were my classes, these would be my frequencies, and these would be my midpoints. So if I average 150 and 180, that's going to give me a midpoint of 165. 180 and 210 is going to give me an average of 195. 210 and 240 is going to give me an average of 225. 240 and 270 is going to give me an average of 255. 270 and 300 is going to give me an average of 285. And then for the last class, we end that class at 329.99, but the next class, if there was a next class, would start at 330. And so if I average 300 and 330, that would give me 315. So if I wanted to create a frequency polygon, then what I'm going to do on the horizontal axis is I'm going to use the class midpoints. So I would use 75 here, 105, 135, 165, 195, 225, 255, 285, and 315. Now, above the tick marks for each of those midpoints, I'm going to go to a height of the frequency. So for 75, the frequency is 1, so I'm going to put a dot right there. For 105, the frequency is 2, so I'm going to put a dot at 2 above it. 135, the frequency is 15, so I'm going up to 15 above that. 165, the frequency is 5, so I'm going to go up to 5. And then 195, the frequency is 11. 225, the frequency is 9. 255, the frequency is 5. 285, the frequency is 1. 315, the frequency is 1. So then what I'm going to do once I have those points plotted, I'm going to just connect those. So I'm going to connect this point here with this point, and then with the next point, and then with the next point, and so on, and so on, and so on, and so on, and so on. Now, one thing that we do here that we didn't do when we were doing histograms, before the first class midpoint, we're going to go to what would have been the class midpoint before it. So I don't know if you paid attention or not, but for my example here, I have it increasing by 30s each time. So if I take 75 and decrease by 30, that would be 45. So here where 45 would be, I'm going to put a point on the axis, and I'm going to connect that. Likewise, I'm going to come to 345 would be the next midpoint if there was a next midpoint. So this would be 345. I'm going to put a point there, and I'm going to connect that. So that's indicating the frequency here would be 0. The frequency here would also be 0, and this forms our polygon. So what's the benefit of doing a frequency polygon instead of a histogram? There isn't. There isn't really a benefit. It's just an option. So we could organize our data like that if we wanted to, and we could use this kind of a graph instead of a histogram. It does essentially the same job that a histogram does. So I can look at it and I can tell if it's bell-shaped or skewed left or skewed right or bimodal or what have you. Another way of organizing the data that is done sometimes will be to organize the data into cumulative frequency distributions or cumulative relative frequency distributions. Well, in a cumulative distribution, we're going to accumulate the frequencies or the relative frequencies as we go from each class to the next. So we're going to continue to aggregate the frequencies or the relative frequencies. So a cumulative frequency distribution displays the aggregate frequency of the category. In other words, for discrete data, it displays the total number of observations less than or equal to the category. For continuous data, it displays the total number of observations less than or equal to the upper class limit of a class. We'll do an example in just a second. A cumulative relative frequency distribution displays the proportion or percentage of observations less than or equal to the category for discrete data, and the proportion or percentage of observations less than or equal to the upper class limit of a class for continuous data. Well, construct a cumulative frequency distribution and a cumulative relative frequency distribution using the parking and camera find data from section 2.2. So again, I have this data already in classes. I have the frequency, I have the relative frequency shown here. And in this case, I was using 60 as the lower limit of the first class and 30 as the class width, which is different from what we did when we did this problem back in section 2.2. Anyway, if the frequency from 60 to 89.99, if the frequency is 1 for that class, then the cumulative frequency is also going to be 1 for that first class. If the frequency for 90 to 119.99 is 2, then the cumulative frequency is going to be those 2 plus the previous 1. So 2 plus 1 is 3. So the cumulative frequency for this class is 3. For the next class, if the frequency is 15, then the cumulative frequency is going to be those 15 plus the previous 3. So the cumulative frequency is 18. So next, the 150 to 179.99, the frequency is 5. So we're going to take that 5 plus the previous 18. The cumulative frequency is 23. Next, the frequency is 11 plus the previous 23. So that's going to be a cumulative frequency of 34. 9 plus the previous 34 gives us a cumulative frequency of 43. 5 plus the previous 43 is 48. 1 plus the previous 48 is 49. And 1 plus the previous 49 is 50. So these are the cumulative frequencies. And so if I have my classes with the cumulative frequencies, that makes up a cumulative frequency distribution. The cumulative frequency of the last class should be the number of data values. So we had 50 data values, so the cumulative frequency is going to be 50 for the last class. Cumulative relative frequency works the exact same way, except using the relative frequencies. So the first class, the cumulative relative frequency is going to be just the relative frequency of the first class, 0.02. For the second class, I'm going to take its relative frequency, 0.04, plus the previous 0.02. So the cumulative frequency is 0.06. For the next class, I'm going to take the relative frequency, 0.30, plus the previous 0.06, I should say. And so the cumulative frequency is 0.36. For the next class, 0.10, plus the previous 0.36 is 0.46. Next, 0.22 plus the previous 0.46 is going to be 0.68. 0.18 plus the previous 0.68 is going to be 0.86. 0.10 plus the previous 0.86 is 0.96. 0.02 plus the previous 0.96 is 0.98. And last but not least, 0.02 plus the previous 0.98 is 1. So our cumulative frequency of the last class should equal 1. Now, what's the benefit of using a cumulative distribution instead of just a regular distribution? So why would we use a cumulative relative frequency distribution instead of just a relative frequency distribution? Well, sometimes we may want to see how data is aggregating. How's it accumulating? So that's the point. Not used as frequently as like a regular old frequency or relative frequency distribution, but you will see these. at times. Now, so we have the distributions. We can create graphs of those distributions. So we can create a graph of the cumulative frequency distribution, or we can create a graph of the cumulative relative frequency distribution. And the graph that we will usually use for the cumulative frequency or the cumulative relative frequency distributions is called an ogive. So an ogive is a graph that represents the cumulative frequency or cumulative relative frequency for the class. It is constructed by plotting points whose x coordinates are the upper class limits and whose y coordinates are the cumulative frequencies or cumulative relative frequencies of the class. Then line segments are drawn connecting consecutive points. An additional line segment is drawn connecting the first point to the horizontal axis at a location representing the upper limit of the class that would precede the first class if it existed. So we want to construct a cumulative relative frequency ogive using the parking and camera finds data. So cumulative relative frequency ogive means we're going to be using the cumulative relative frequencies. So along the horizontal axis, I'm going to be using the upper limits of the classes. And on the vertical axis, I'm going to be using the cumulative relative frequencies. So notice that I'm going like 0.2, 0.4, 0.6, 0.8 to 1. Now here, I'm going to start at the second tick mark, and I'm going to make that the upper limit of my first class. So this is going to be 89.99. And then my next tick mark is going to be 119.99 and 149.99 and 179.99, 209.99, 239.99, 269.99, 299.99, and last but not least, 329.99. So I'm always using, for an ogive, I'm using the upper limit of the classes. Now, if there was a class that came before the first class is starting at 60, so the upper class limit that would come before that would be 59.99. I'm also going to mark this 59.99. That's my first tick mark there. So now for the first class, the cumulative relative frequency was 0.02. So that was 0.02. So above the 89.99, I'm going to go up to 0.02, and 0.02 would be maybe like around here. And I'm going to put a point. And then next, for the 119.99 class, the cumulative relative frequency was 0.06. So I'm going to come up to 0.06, which would be maybe around in there. For the next class, the cumulative relative frequency is 0.36. So that's going to be up around in there. Next is 0.46. So maybe around in there. Next is 0.68. So not quite halfway between the 0.6 and the 0.8. The next is 0.86. So again, not quite halfway between the 0.8 and the 1. 0.96 is next. And so that is a little past halfway. And then 0.98. And then 1. So I plot those points and I connect them with line segments. So again, the point of this is that I'm seeing how the data is accumulating, which is why it's called cumulative. And I do connect that first class with the horizontal axis. So like right there. So again, I can see there wasn't any data at this point, and then it starts accumulating. So again, what's the benefit? Well, if you're wanting to see how data is accumulating, then this would make more sense to use than just a regular old histogram. So again, less commonly used, but we will see them on occasion.